Today I want to talk a little bit about how pandas and Dask are integrating more deeply with PyArrow and Apache Arrow in general, and how this is changing both projects pretty deeply. First, a little bit about me. I am currently working at Coil. Coil is a company where we deploy Dask in the cloud, but I work on our open source team and focus mostly on the development of Dask. A couple of the things I'm showing today is something I've been working on for months now. I am a member of the pandas core team for close to 3 years now, and was involved in the Arrow integration that we published with the 2.0 release a couple of months ago, earlier this year. I'm assuming that most people here know pandas. It's a data analysis library that is a little bit popular. The second part of the talk will focus on how we can scale pandas to bigger workloads. One possible option is Dask, specifically the Dask data frame API. I won't focus on anything else today, just the data frame integration. Dask in general scales PyData libraries and specifically pandas, which is a big part of what I'm focusing on at work. We have a lot of topics today. We have a lot of ground to cover. We will start with Arrow integration as a backing of data frames. And we'll focus a little bit more on strings than the other p-types because they offer a lot of benefits. Then we move over to copy and write, which is a new feature in pandas that will hopefully, for one, speed up performance, and two, make the behavior of the API more consistent and easier to identify for users. The third thing is specific to Dask. Shuffling is something that you need in a distributed system that doesn't really matter for pandas at all. There's a lot of work going on in Dask to make this more efficient, more stable, generally a better user experience. And then what I'm currently working on is a query optimizer for Dask data frames. There are some loose plans to also adapt this for pandas in the future, but we want to first focus on to make this work for Dask before we think about anything else. I have a couple of demos today. They will mostly use Dask because Dask demos a lot better than pandas, simply since the workflows take longer and are larger. We will start with an example that illustrates how Dask behaved 6 months ago. The query I'm running, it's not super important. It has two merges, which involves a lot of shuffling, and a group by aggregation. Dask was historically not very good at this. And we will shortly see why. These are the operations that we're focusing on to make them more efficient. In the end, we will see how this changed over the last couple of months. So on the right side, what we can see here is, in the top, this is what's going on in our Dask cluster. This is basically a pandas-like workflow in a distributed way. A Dask cluster is generally happy if you don't see a lot of white and you don't see a lot of red, which is both things that we have quite a lot here. So this is a workload that's not ideal. It operates on 100 gigabytes of data on 20 machines, so in theory this should be pretty quick. But because of some historical issues with Dask, this takes a long time. And we can see how the red grows. Down here is the memory usage on the cluster. This also goes up quite a lot. If we wait until the workflow finishes, then we will run into the red area here and in the end kill some workers, which is not ideal. But I only have 40 minutes, so we don't have 2 minutes to wait here and see how the cluster kills itself. A lot of the things that happened in pandas and Dask over the last year and a half, have enabled us to get rid of this. And we will later see how we can run this workflow 10 times faster with a lot less memory pressure. But before we can get there, we have to build some theory. So we're going back to the slides. First part is the Apache Arrow integration in pandas and Dask. Arrow initially was founded like in 2015 by the pandas founder as well. And over the last like 3 or 4 years, the pandas project moved a lot into the direction of better integrating Arrow with its API. And now we will see what this means for users. The whole talk assumes that you are using pandas 2.0 or later. Anything before that is like a long time ago for us in development cycles. My opinion, the biggest advantage of Apache Arrow for pandas is that it has an efficient string data type implementation. Historically, pandas used NumPy object type to represent strings, which is for one slow and two super memory inefficient. Like memory just blows up if you have a lot of NumPy objects. But there isn't really an efficient string data type in NumPy that we could have used alternatively. That's why we fell back to object. Arrow changes that for us a lot. They have a string data type that's contiguous in memory, so we don't waste any bytes that we don't need, and it's also super fast to operate on. Arrow comes a lot with compute functionality for stuff that has historically not been available in NumPy. They have a lot of compute functionality that you can dispatch to, so we can and will rip out some of our custom implementations to reduce the maintenance burden, and also just dispatch more efficiently. I think most people know this. If you have a pandas integer column that's NumPy backed, and you try to insert a missing value, you will lose the integer column, and it will get upcast to float, which, especially in finance, for finance history, is very annoying. Arrow also changes that. Arrow has nullability by default for every d-type. So if you want to insert missing values, it will just keep the d-type consistent. Also, we can just represent a lot more data types. Like if you have bytes or decimals or nested data like structs or lists, all of this is object in pandas. But in Arrow, we have specific data types for that. So for one, the implementation is more efficient, and two, memory usage is a lot lower than it would be in NumPy object. This is the biggest advantage at the moment for us. All these different data types, and they have consistent UX. If you do a lot of numerical calculation and you have only float columns, then Arrow won't help very much, since NumPy is very, very optimized in that area. But as soon as you have different data types that don't fit into the integer or float area, then Arrow becomes way more valuable to users. Also, there's another thing, like there's Polars now, DuckDB, PySpark, they're all backed by the Arrow data model. So if you want to move your data from one data frame implementation to another, using this with Arrow is zero copy. Going from NumPy to Arrow might be zero copy, but it's probably not. So you will trigger copies at some point. This is a quick view into the future. Pandas 3.0, which is we expect to come out early next year, will start to infer arrow-backed strings by default. So you won't get NumPy object anymore, except if you have like mixed columns. If you have strings and integers, then you will still end up with NumPy object. But if you have columns that are purely strings, then this will just be an arrow-backed string without any like user effort. This will just be the new default. This new string data type will behave as NumPy object. So we changed the semantics of arrow a little bit to just reduce the migration burden on users. So just the same code statement. You instantiate a data frame with like string columns. Right now you get object d-type, and in Pandas 3.0 you will get an arrow-backed string d-type. No change required, hopefully. This is already available, starting with Pandas 2.1, not 2.0. There's an option that will enable this new behavior. So if you want to get this behavior right now, you can just turn the option on, assuming you're on Pandas 2.1 or later, and then you will get rid of NumPy object data. Another advantage over like casting yourself is that all I/O readers will automatically use this d-type. So if you, for example, read from Parquet files, right now you would go to object, and then you would have to cast back to arrow strings, which is slow and like memory inefficient. And if you set this option, all of this will happen by default. There won't be an object string launcher anymore. Dask is a very similar implementation. but we are already using them by default. We made the switch already. So if you instantiate a Dask data frame, you won't end up with an NumPy object anymore. We have seen better performance, but to be honest, most Dask users don't care that much about performance. They care more about memory stability, which is a huge improvement. Like, we've seen memory usage on like data sets with a couple of string columns like reduced by 50 to 60%. If you have more string heavy data sets, then this decrease will be even heavier. We would in a few seconds see a demo how this looks like. As I said, it's used by default since July. So if you're on a newer Dask version, you will get this behavior by default. Dask has an option, convert string. This is on by default. So if you want to see the difference between both variants, then we'll have to turn it off, obviously. So if you load this now, then I probably should have restarted the cluster. We will see how quickly the memory usage grows here. Also, the reading is pretty slow because the string to object conversion is especially disadvantaged in multi-threaded environments. We can see that our cluster here, the memory usage is growing. These orange bars says that we are in a critical area where Dask will start spilling to disk, which is something you won't want because that will just make you slow. I will kill that data frame now and restart my client so that we don't have to wait until this is finished. Spilling to disk is very slow. So if we set this option to true, then we will notice two different things. For one, the reading is way faster because the conversion from Parquet to Arrow to Dask is just 0 copy. And the even more impressive thing is like the bars down here. There's no memory pressure on our cluster. It just fits very easily. This either saves cost or brings you a lot of stability. We only have like 4.5 gigs in here. Previously we had over 10. So this is roughly a 50% to 60% decrease. The impressive thing here is that we only have 3 string columns. Everything else is like not touched by this option at all. The categories here have some string columns as well, but they have like 3 flags, like yes, no, and NA. So the arrow strings won't really matter here. It's just these 3 string columns that reduce our memory usage by 50%. If you have more string columns, then this will be more drastic. So we'll just scale the cluster for the next step. The second bigger thing that we expect for 3.0 is that we will change copy and view rules in pandas. Right now, this is a pretty big mess, in our opinion. Users might disagree, but I haven't found any. We want to have more consistent copy and view semantics in pandas, and we call this copy and write. This is something that's popular more in the low-level world and a bit tricky in pandas, but I think we can make this work. Or I like to call it like getting rid of the setting of copy warning. The setting of copy warning is like an old friend for most pandas users, I guess. Or a foe, I don't know. Like I've run into this like on my first week using pandas. And I really didn't understand what was going on until I started maintaining the indexing engine in pandas. So yeah, I'm sorry for everyone who had to suffer through that. Copy and write will change pandas in a way that the setting with copy warning will go away. It won't be necessary anymore. So all the blog posts that are out there trying to explain to you what the setting with copy warning is can be deleted after this. What this does right now is if you subset a data frame, this is a Boolean mask. Like if you filter for something that's greater than 1, then this will trigger a copy. Pandas thinks that you might have wanted to update df as well. So we try to be intelligent here. And so we tell you, yeah, that this doesn't work. But most users probably don't care that df isn't updated. They just want to update subset and then they're fine. So what most people do, like at least in my experience, is they add a copy in that line, which will trigger another copy. It's a little bit annoying if your data frame is large. Like if it only has a couple of rows, then it doesn't matter. So what we are aiming for is that every data frame or series that is created from another pandas object behaves as a copy. We don't actually do a copy, so not every operation will create a copy, but they will try to behave as it would be a copy. So if you try to update this new object, the parent won't be updated anymore, even if it's a view on the delivery. So there won't be an operation in pandas that will update two objects at once. That won't be possible anymore. You only update the object that you're operating on. Our opinion, this has a couple of advantages. The user experience is more consistent and simpler. You don't have to worry anymore about copies and views. Pandas will just take care of this for you. And we try to be as efficient as possible and only have to copy when it's necessary. As I said, setting the copy warning is in the past then. We already have a working implementation for copy and write that's basically finished. And the setting the copy warning doesn't matter then anymore. Like the complete history runs without. There won't be a confusion anymore if you are mutating two objects, or 3, or 4, or 5, or only one. Copy and write will take care of that for you. Another advantage that I personally like even more is that we don't have to do defensive copies anymore. At the moment in pandas, if you have a data frame that has like 50 columns and you drop one column, you might expect that this is a view and we just like remove that column from the data frame and give you back a new object. But that's not what we do. Like, we copy all the columns, like a deep copy of the data. If you then like rename all your columns, don't touch the data at all, we again deep copy of the data. This goes through basically all operations that don't change the length of your data frame. Every operation even copies the columns you don't touch. Like as typing one column, you copy all the others. This is because if you wouldn't do that and you would do an in-place modification afterwards, you might update 20 objects at once. And I wish you good luck debugging that. It's not fun. This is one of the reasons why copy and write is, on some operations, very, very fast compared to the previous implementation. Like you have a rename here, and then an assign, drop, as type, reset index, set index. None of this actually changes the length of your data. Like NumPy triggers copies if you change the length of your data, but none of these actually do. The current implementation copies for all of these statements. With copy and write, we get rid of these defensive copies. So the running time is constant. It doesn't matter anymore how long your data frame is. It will just be like some metadata casts that happen under the hood, but your data is untouched. This won't help if you do like group by aggregations and stuff like that, because that will need copies anyway. But if you do a lot of like modifying of your data frame before you actually aggregate at some point, then this will speed up your code a lot. One of the core devs ran this on a like proprietary code base, and he saw like 60 to 70% performance improvements over the current implementation that they are using. It was also running for like 10 minutes, not like we got down from 2 seconds to 1. That wouldn't be that impressive. We'll get back to this later, but you already can try this out. The implementation is basically finished. There aren't any bugs that we are aware of. Like, there might be some that we don't know about. But from our point of view, this is finished and could go live now, but we have to wait for 3.0.
Sorry, you said this is coming in 2.1, or is it already?
This is available in 2.0, and you can use it. I would recommend upgrading to 2.1 though. And with 3.0, it will be the default. There won't be a non-copy and write mode. So if you like updating multiple objects at once, you have to find a different solution. We will now move over to Dask data frame in a bit more detail. The theme of this is like that Dask data frame is faster. We will see in a little bit why this is true. We will specifically talk about a new shuffle algorithm and how we introduce query optimization to Dask data frames so that we can just avoid doing unnecessary work. And then we'll watch another demo, how this looks in comparison with the previous implementation. So we start with the shuffle algorithm. The previous shuffle algorithm that was the default until earlier this year was a task-based shuffle algorithm. And what we can see here, we just had a bunch of inputs and a bunch of outputs that were on different workers. And to get to the output state, we had to create a lot of intermediate tasks. This scaled with n times m, where n is the number of input partitions and m is the number of output partitions. So in the worst case, you had a quadratic growth of intermediate tasks. And if you have to schedule millions of small tasks, then the Dask scheduler will just pack and slow your cluster down by orders of magnitude. The new shuffling algorithm gets more or less completely rid of this intermediate layer. There's only one task. Doesn't matter how big your data frame is, how many partitions you have. All this complexity is now hidden away in a different system that doesn't strain the scheduler. And it's also a lot faster in general. But we are also not pinging the scheduler anymore. So this means for us that we have significantly improved performance. We can now utilize all resources in our cluster. Before that, if you had a huge cluster and just in a huge data frame, we were probably utilizing 5% of your available CPU. Now we are more at 60 to 70. And the remaining stuff is blocked by disk writes.
So does that mean you're multi-core now in Dask?
Dask has always been multi-core and multiple machines.
Even on a single machine?
Yes. Yes, you can utilize all your resources on. If you have an HPC with 100 cores, Dask can make use of all of them.
So, are you centralizing then? How are you scheduling the shuffling? Is that what you're trying to show?
The input tasks are just sending the data to the output workers without telling the scheduler about this. This is hidden away in a system that's not straining the scheduler as much.
Okay, so directly to the...
Yes. We are not going through scheduling millions of small tasks anymore. The P2P shuffle, this is the new shuffle algorithm. We can see here that data usage, memory usage is very, very low. We can shuffle at constant memory, while this one is packed at orange, which means that we're spilling to disk. This is the gray part here. And this is a dashboard you wanted to see on the right side, less white, and all workers are constantly busy. While this here is a lot of white, which means that workers are idling and don't have anything to do. We generally can now shuffle data at constant memory. Previously, this was growing linearly, and at some point, your cluster was killed if you didn't account for that. The blue line is the new P2P shuffle. It's just constant at 5 gigabytes, and then when we unpack, there's a small spike. But this was actually a bug, which is fixed now. And the old task-based shuffling just goes up linearly, and then 25 gigabytes is, this is per worker, it's actually quite a lot. So this will increase stability by a lot compared to the previous implementation of task-based shuffling. This has been enabled in March this year, and is now since used as the default. We haven't seen many workflows that actually want to use task-based shuffling. Most of our users switched over to P2P shuffle. The thing that we're currently working on that's not yet enabled by default is query planning in Dask. Historically, Dask was just executing what you gave it. So if you were reading a whole data set and selecting one column, Dask was reading the whole data set and then dropping all the others. Which is especially annoying if you're reading from S3 or somewhere where latency is high and data transfer is not super fast. We are slowly getting rid of all of these problems now. We will just quickly start with a short example and see what the query optimizer can do for you before we go into a bit more technical details and then look at the demo. So this is a query someone might write it. We read a whole Parquet file, filter for one specific value, do a sum, and then we select one value. Dask currently would still read all of your columns, all of your rows, and then it will do everything in memory. If your data set is large, this is pretty annoying. So what a query optimizer normally does is it looks at your query, identifies which columns you will need. In this case, it's X and ID, and restrict the read from storage to these columns. But that's not all we can do. Like, we're still aggregating ID and X, which is something like we don't need. So we can move the projection of X in front of the sum, so that we only have to like aggregate one column, not two. Given that's a small advantage, but if you have lots of columns before that, might quite make a difference. But we're still reading all rows for these two columns, which also is not necessary because Parquet supports filters in the I/O read, so that you don't have to load all data in the memory. So this is something you can do as well. This is a bit tricky because this is not always efficient. If your data is not sorted, for example, there is no information about your data available, this might slow you down, but it will still keep your memory usage lower, significantly lower in this case. The change is pretty small. The API mirrors the Dask data frame API. It's still a separate project, but we will change that hopefully soon. And then it will be integrated with Dask data frame, and it's on by default. But right now it's a different project that just mirrors the Dask data frame API, and like an optimized step is injected between actually like getting the query and executing it. Some background why we're doing this now. Historically, what Dask was good at is flexibility on the scheduler and smartly scheduling tasks to your different workers. So Dask was able to basically create task graphs from every random query you could think of. Like if this was very complex and had like different dependencies on each other, Dask was able to figure this out. This was like our main selling point against something like Spark. But if you do SQL-like stuff, these things don't matter as much because your queries can only get so complex. So Dask always had this like physical optimization plan, while Spark had the high-level logical plan that was just dropping unnecessary work. And that's why we're building this into Dask. Took a long while, to be honest, but now we are finally getting there. This will make us a lot faster on like common workloads. We will see in a little bit how much we actually can improve performance here. All the things that we're doing here could be done by the user, obviously. Like query reordering is nothing that's like magic, but most users either don't want to think about this, which is totally understandable, or if you have thousands of columns in a very complex query, optimizing this by hand is like pain. So this is where the query optimizer comes in handy. It just does this automatically for you, and you don't have to think that much about writing efficient code anymore. Still have to think a little. So now we can look at a quick example. I prepared like 2 Dask clusters here. Each of them has 20 workers. On the right side is the old version, which uses task-based shuffling and the current Dask data frame implementation. We will give this one a little bit of a head start. And on the right side is the new version with P2P, the new shuffle algorithm, and the query optimizer enabled. And now we can start this as well. And the first thing that we can see here, we have like 62,000, hopefully that's readable, 62,000 tasks of this intermediate layer that I was talking about earlier, which is quite a lot. We can see that over here, the whole query, this is the optimized query with P2P shuffling, just has maybe 15,000 tasks in total. So only the shuffle step has 4 times as many tasks as the other query, complete other query. This is connected to the wrong dashboard. That's interesting. But what you can see here, like the right side is already like finished and basically chilling in the locker room, while the left side is still pretty busy. And like, if you want to wait for another minute, then we'll see that this will get into memory problems and slow down even further. What we've seen is like, this is on 100 gigabyte. This is a size that we could benchmark pretty good on. We've seen like 5 to 10x improvements. If we increase the size to 1 terabyte, Dask data frame was either not running anymore because it was running out of memory, disk space was used, stuff like that, or we were like 50 to 100 times faster. So if we would scale this out to 10 terabyte, 100 terabytes, the Dask data frame probably wouldn't be able to handle this anymore, while our Dask expression implementation is just running along happily. Obviously gets slower with more data, but we can still complete the queries easily. Things users can do now that will hopefully improve their life and their UX. And we can enable copy and write. That's just a simple flag, and then you will use the new semantics. I would run the test suite after this. Some things change. Then you can enable the infra-string option that just will give you arrow back strings by default. Copy and write is available since 2.0. Infra-strings are available since 2.1. So you need the newest version for that. And if you're a Dask data frame user, if you do anything new, we would recommend switching over. Like, it's currently a separate library, but we will move this into Dask data frame at some point, hopefully not too far in the future. It's just a plain Python library, it doesn't bring in any dependencies, so it's an easy install.